let's get started with this topic. And yeah, if any of you ever have any questions, please feel free to ask them right away. We're not yeah, I don't have a strict schedule or anything, and I think we can make this very flexible. You can yeah ask your questions as soon as you want. Cool. But yeah, we're talking about the machine learning for modeling biomolecules here. And sorry about that. I just have to move some Zoom stuff away. Um, and first of all, I wanted to say why I think this is a particularly exciting area for machine learning, uh, for geometric deep learning, for graph machine learning. And that is because the potential for positive impact is so huge in in this application or in this application field in biochemistry. There are areas like drug discovery, like material design, like protein design, where if we discover a new drug, of course, this can be hugely important. If we develop better solar cells or better materials for solar cells, then maybe we can help fight climate change. If we find a protein that connects to, or that's better at connecting to some other protein and then inhibits the function of that other protein, and then maybe you have a maybe this protein then is essential for the survival of some bacterium, and if that can no longer function, then we kill the bacterium. We can use that as a drug or maybe as a vaccine. Yeah, so I think the geometric deep learning and applications in biochemistry are extremely exciting because there's so much positive impact possible. And it's not only that there are interesting problems and super important problems, but we've also even seen that they can be addressed, and there can be something positive. There are solutions with machine learning that are valuable here. And two that I maybe want to really highlight here, that you might very well also have heard of already, is protein folding with AlphaFold, where in 2021, I guess, or 2020, their AlphaFold won the CASP challenge. So what is it called? Assessment of structure prediction something, or complete assessment of structure prediction. And it's about predicting the structure that into which a protein folds, right? Proteins are these things swimming around in our body, basically doing everything and every function in our body, and making up, for example, also our skin, or making up the walls of our cells, and making up our cells themselves, basically. And yeah, the protein structure is what informs how they function. And now people have tried predicting the structure of proteins and using some calculations with force fields and other physics-informed methods to fold proteins together or find out in which structure they arrange. But this was just a long-standing challenge and a completely unsolved task, right? And now AlphaFolds came along and they were the first ones who were able to make the predictions on this competitive assessment of structure prediction, which is held every 4 years, I think. And they were the first ones who were able to make predictions at a sub-angstrom level of accuracy, and that means like they just were able to do it at the desired level of accuracy that you need, or that biologists want, maybe. Yeah, and there we can be sure that this was maybe this is even the most impactful application of machine learning in the sciences. Yeah, and of course they definitely use some graph techniques to encode the proteins and geometric deep learning methods that we'll have a look at. Okay, and then there's also another example here, this antibiotic called halicillin that was discovered in 2020. And there they were actually using graph neural networks to predict the properties of molecules to then help search through those molecules faster and find drug candidates, such as the final antibiotic, which then was halicillin. And it's actually apparently one a pretty good, what do you call it? A pretty good antibiotic. Okay, then how do we represent molecules? So right, we say we now want to do our geometric deep learning for molecules, and this, or no, let's say we want to do machine learning for molecules, and then how do we represent our molecule is a question. What many people did was representing molecules as a string of letters, but maybe that is not actually the ideal representation. And what else you can do, like maybe a much more natural representation as well, is with a graph, right? Molecules are essentially graphs. You have your atoms as the nodes, and you connect them with edges based on the bonds between them. And yeah, this is a graph. And now we can use a GNN operating on that to make our predictions. But then let me quickly ask again, like, how familiar are we here now with graph neural networks and processing on graphs? Can someone let me know about that? Because based on that, that will decide how detailed I'll make my graph neural network explanation now. I see something was written in the chat that unfortunately my mouse isn't really.
They say unfamiliar, both.
Unfamiliar. Okay, that's good. Then let's go with our graph neural network explanation after I introduce these other graph notions. So, right, because in can you see my cursor now? Yeah, excellent. Because in applications, often we don't only have the 2D structure here of the molecular graph, we sometimes also have 3D coordinates, where each atom not only is associated with its atom type, but it's also associated with a 3D coordinate, right? And the 3D structure of the molecule can give us a lot of valuable information of how the molecule operates and what's going on. And in that case, if we have the 3D coordinates as well, then what we often do is to build a radius graph. So we just connect each atom with the closest by other atoms that are within a particular radius of that first atom. And this way we build our graph, right? So now we have, and then the edges of this graph can be associated with the distances between the atoms. Yeah, and this way we have two options to represent molecules. But here we are today also want to talk a little bit about larger molecules than just these small molecules, and particularly about proteins, right? So over here, like proteins are these large molecules that are swimming around in our bodies, and well, what distinguishes a protein from another small molecule, it's just that it's made up of these 20 amino acids, which are like building blocks, and they are arranged in a sequence, and based on this sequence, like if you choose another sequence, then this 3D structure that the protein will take on will be a different one. Yeah, and now we could also represent our protein in the middle here as a graph, as we did with the small molecule, where we just take every single atom in the protein and we connect the atoms with each other if they are within a particular radius. But most of the time, what we actually do is I said the protein is made up of these 20 amino acids, and we actually only consider the amino acids. And then we have a graph that or a structure that sort of looks like what we have over here on the what we have over here on the right. And yeah, this way we have much fewer nodes and can maybe do our computations in a much more computationally efficient way, because maybe not the full resolution is required. Okay, but then I would just quickly connect with my iPad to explain our graph neural networks here. So we now know how we represent our proteins, right? And how we construct the graphs with which we represent our molecules and our proteins. But now, how do we process them with graph neural networks? But for that, I guess I need to log into this tryvirtually.com to get the Zoom link over here as well. And if you have any questions, please feel free to go ahead as soon as you want. Okay, if you could let me into the meeting room with my tablet as well, that would be great. And then we can go ahead. Got it. Okay. Then I will just share my screen over here. Great. So, because we now have these graphs of our these graphs of a small molecule. Let's say this is right here. This is our graph, right? And we remember these are maybe our atoms, or these are our atoms, and they are associated with an atom type, which, like, is it a carbon, is it an oxygen, hydrogen, nitrogen, ... And they can also have many other features, like the electronegativity. You can have the number of cycles that they are contained in. and this would be 1 for this one and 0 over here. And yeah, you can also have then our bonds and features of for our bonds. Like if these, for example, are double bonds in our molecule here, then maybe we have as features that, yeah, these are double bonds and these are single bonds. And we can also, again, add to our bonds the features whether or not they're in a cycle, right? But now, if we draw a molecule again here, if we have our molecule with its features or featurization as we just described it, with the edges and nodes in our graph, then we can use something like message passing neural networks, or yeah, we can use GNNs to process them, but the framework that I'm going to highlight now, because a lot of methods, a lot of GNNs fit under this hood, those are message passing neural networks. And what we do there is, right, we have our feature vector over here for the node. We have our feature vector over here for this other node. And now we have a GNN layer that wants to update these feature vectors. And we also have some edge features here, but those we are not going to update. We're just going to use them to update our node features. So what we're going to do there is, let's just take node feature I, node feature J together. We concatenate them, and then we feed them through some neural network and end up with a new vector. And then, yeah, we can also do that for, we can additionally, sorry about that. I hope I'm still in the Zoom.
You're not. I think you're not sharing anymore.
Okay. I guess I need to reshare. There we go. And we can additionally append our edge features here and feed it through the neural network, right, to include our edge information. And then we end up with this updated vector here that contains the information of our node features and of our edge features. Let's call that MIJ, the message between I and J, between node I and node J here, right? So we create these messages, but we don't only do that for this edge right here. We also do that for this edge, this edge, this edge. So, and like for every edge. So let's maybe call these these nodes I, J, K, L, and N. Then to update the feature vector, let's maybe call it X, Xi, right, of this node right here. We take the sum of all of the messages that we created with our neighbors. So that would be M, I, and then let's say these, we have the V in the neighbors of the node I. So we sum over all of the, we sum over all of the neighboring vertices, the neighboring nodes, and the messages that were created between them, right? Here we have the message MIK, the message MIL, the message MNI, or the other way around, MIN. And then we sum all of them together, maybe put them through another neural network, and we end up with the updated features here for node number I. But we do that, of course, for every single node, also for this one, and this one. And that is how we do one update step for every single node feature in our graph, right? So this way, we have constructed our graph, a single graph neural network or message passing neural network layer, which is a graph neural network. And we just repeat that a bunch of times. And in the end, we have our fish molecule, and it has some updated node features that hopefully now contain from a lot of information about the molecule and how it could function and what atoms are where. And oops, yeah, let me just draw these features here. And what we do in the end, if we maybe want to predict a property of the whole molecule, right, then we just go ahead and pool all these features together. We just take another sum, or we do mean pooling, or we do max pooling, or we do all of them at the same time and pool them together into another feature vector and have another neural network that maybe projects it down to 10 dimensions. And if we have 10 different classes of molecules or 10 different classes of a specific property that we want to predict, and then we have our final vector, and we can, for example, do some supervised training here. Okay, but now before we can of course also do that for large proteins and so on. But now before we move on, I also quickly want to talk about what people often do when we have 3D information, right? Then we additionally have some positions associated with our nodes. And what we usually do is that we just look at the distances between those nodes as additional edge features. So, and then we encode them in some way, these distances, and use them as additional input to our neural networks, right? Here, where we said that we have this edge feature that we additionally concatenate to our input to the neural network, there we now additionally have the distances encoded in some way, and give our graph neural network information about the 3D structure of the molecule that way. Okay, that would be my quick GNN overview for this purpose. Right? And now, if we have any questions, let's get into them. But otherwise, we would get back to our slides after I leave this room here and do this one. And I'll also have a quick check of the chat. That was just unfamiliar. And I'll press play if Zoom goes away. Hide floating meeting controls. Nice. And then I can press play. And we have our graphs here, as we discussed. And now I want to highlight like different, give an overview of different areas where these graph neural networks, as we just explained them, and additional geometric deep learning methods are being applied in molecular machine learning, say, machine learning for biochemistry. And there I want to start with molecular property predictions, which is maybe the most straightforward thing, right? This is what we just mentioned, where we were pooling the features and then could just predict a single property, for example. And there, one of the founding, or one of the seminal works, maybe in my opinion, is called neural message passing for quantum chemistry, and that was in 2017, where actually, like, this work coming from chemistry, right? They introduced the message passing neural networks framework, and this is now something that's all over the GNN literature. So they really brought forward the field of chemistry or quantum chemistry, and their search for solutions for their problems. That it really brought forward the field of geometric machine learning and graph machine learning in general. So coming from this application side, we had advancements in with general methods that are now very generally applicable. And what they did is to predict the quantum properties of a small molecule, as we just described it. So when I say quantum properties, these are properties like energies, right? And yeah, the energy of the conformation of a small molecule. So these energies, they are associated with a 3D structure of a molecule. So here we're talking about the case where we do have the 3D structure of a small molecule available, and also, for example, use the distances as additional edge features, which is what they did. Okay, but then I also want to get to proteins, right? We said we don't only have to operate on small molecules. We could also have a graph neural network operating on large proteins. And in 2021, we had this iClear paper, I believe, where we have just the graph of a protein with the amino acids, as we described, like this coarse-grained representation, but we also have a summary of a more fine-grained representation on the surface, where we consider some atoms close to the surface. And then we have this hierarchical graph, where we have the coarse graph of amino acids connected to the more fine-grained graph of atoms close to the surface. And then we can also, again, do our message passing as we described, and pool everything together and make a final prediction. Like, for example, does this protein catalyze the reaction of a particular reaction? Was that the right sentence? Does this protein catalyze a particular reaction? Is what I wanted to say. So is it an enzyme for a particular reaction? And also, for example, how likely is a protein to interact with a particular molecule? And this is important, right? Because then maybe this molecule might interfere with the protein in some way, and this small molecule could be a drug, or maybe we cannot use this protein because the small molecule has problems with it, and the small molecule is swimming around all over in our body, and then we already know we don't need to consider this protein. Okay, but then let's get to what was called ChemProp, which came from a group here at literally here where I'm sitting right now, where they analyze learned molecular representation for property prediction, right? So they just provide this ChemProp library, where called chem from chemistry and prop for propagation, and there we're talking about propagation of messages in a graph of the small molecule. And so we're talking about message passing and graph neural networks. Yeah, and they introduced this as a new directional message passing neural network, where we would also always consider the direction in which a message is going, basically, or the direction which a message is coming from. And they then used this framework later on to look at many molecules when looking for an antibiotic. Right? There we have a bunch of bacteria, and we have a bunch of data of molecules that are antibiotics for this bacterium, so kill this bacterium, or are not. And then we train our model to predict that. And we take a library of millions of molecules and predict for all of them whether or not they will be an antibiotic or have some antibiotic properties. And then we have a bunch of suggestions of molecules that are antibiotics and have to then test them. Then we have these candidates, right? But of course, it's just a prediction, and then we have to test if they actually are antibiotics. And we need to go through the whole rest of the pipeline for developing an actual drug. Yeah, so this way, this ChemProp library was able, or the graph neural networks used here, they were able to help the discovery of a new antibiotic. And yeah, this is of course amazing, but we also know that this graph neural network application was only a tiny part of the discovery of this new antibiotic, which is called helicillin. And really most of the work was still done by humans, so to say. And yeah, what means so to say? Most of the work was done by humans, and the graph neural network was only a tiny part of the help done for the humans. And we would really like to help out much more. And there definitely are many, many more open opportunities to work on in this area, like generalization to unseen molecules and other unsolved problems. Okay, but this is about molecular property prediction. Now I want to get into molecule design and generation, which is another big part of geometric deep learning for biochemistry. And there I want to start with small molecule generation approach, where these people here at MIT as well, Wang and Jin, they took the idea of generating a molecule by splitting it up, or by generating a molecule by predicting fragments of a molecule that should be contained in the generated molecule, and then predicting where the where the next fragment, so to say, should attach to our initial fragment, and then we build up our molecule step by step by adding more fragments. And this the way that we encode our molecule, or that we predict all of these things, where the next fragment should go and which next fragment should go there, is of course always done with a graph neural network. Yeah, and this is pretty exciting, because this way we can propose new molecules that we may have never even thought of or never even heard of, because the space of potential molecules is so vast, or potential drug-like molecule is so vast. Some people say 10 to the 60 possibilities, right? So we can generate these new molecules that are not only the ones that we're already used to, and in this new space of molecules, we might find other drug candidates. Also, we can condition our generative model on some properties of molecules, and then we can maybe generate molecules that have these desirable properties. And that's, of course, awesome. If this were to work perfectly, then we could say, yeah, I want to generate a molecule that binds to this particular protein, then this is a drug, right? And then we can just generate the drug. But of course, this doesn't work perfectly. And there are some, of course, also many open avenues for future work in this area. Also, if we're talking about generating drugs that bind to proteins, and this is, of course, hugely important because this is basically generating generating a drug, which is what it means to design something that binds to a particular pocket of a protein in many cases. Then we can also go ahead and put a little or start with the pocket of a protein where we think that a small molecule could bind, or where we know that if something binds there, then it would be a drug and might inhibit the function of the protein or increase its function or change its function. And yeah, then we can try, or what many papers now did, as I wrote here, 9 papers submitted to ICLR 2023. So there recently was this deadline of one of the 3 big machine learning conferences, ICLR. And yeah, then I went on the papers, or went to search through the papers that were submitted to this conference, and I find that 9 papers there submitted there, or at least 9, they actually did try to do exactly that, and we're all working on the same problem. So you see, this is a really hot area of having a pocket of a protein and then generating the 3D structure and the atoms of a small molecule that binds to that pocket. Yeah, and then of course we can also again go to the protein world, where Jason Yim, sitting over there as well, he developed a model where we have a fragment of a protein or a piece of a protein which we know does something that we wanted to do, but maybe it's too small to be stable, or it's just not stable because of its structure, and we want to design a backbone around it, or we just have this motif that does something that we wanted to do, but now we want to design the rest of the protein that contains this motif. And there he then used graph neural networks and diffusion models to generate protein sequences that contain this desired motif in the structure that we want the motif to be in. Yeah, and that would be my quick overview of the protein, or my quick overview of the design and generation area. And then I want to get to structure prediction, because there we of course have AlphaFold, which I already talked about in quite some detail. And this is maybe really one of the largest innovations in science that has been achieved with machine learning. So this is, in my opinion, maybe the biggest success in the field of machine learning for biochemistry, or machine learning for molecules. And many people even say that this is one of the biggest successes in biology in recent times. and therefore think that the AlphaFold team might win a Nobel Prize in the coming years. I mean, I have no idea about things like that, but I've heard this being said now multiple times. Okay, but we can also talk about structure generation for small molecules, and there, for example, right? Why do we want to generate the structure of small molecules? Of course, it's also very important, just like the structure prediction for big proteins. And that is because if we have the ensemble of 3D structures that a small molecule can take on, then we can predict certain properties, for example, that the material design requires, or yeah, that's it just tells you about properties. And also these 3D structures are often used in the initial as initial structures that are then employed in when screening for drug candidates. Right? If we have a protein and want to dock or to bind a small molecule to it, then the small molecule often needs to have an initial structure, and we can now generate this with this molecular conformer generation method. And what they did there is to only change torsion angles, or they only generate the torsion angles of a small molecule, because the bond lengths and bond angles of a small molecule are already clear, basically, or that they are very rigid and well determined, and predicting them isn't the hard part in most cases. And they do that with a diffusion model over the torsion angles of the small molecule. Okay, and then lastly, I want to talk about molecular dynamics, which is an area where there maybe hasn't been so much progress with machine learning yet, but it definitely has already been looked at a lot, and maybe it's one of the most exciting opportunities for machine learning methods and geometric machine learning to make progress in the coming years. And there we, for example, can look at this paper which introduced NeQuip, and there they just have a graph neural network as we described it. It is running, or it has the graph of a small molecule as in the drawing over here, and it has the graph of some material, right? And we also have the connections between the small molecule and the material based on the distances. Now, maybe first of all, I should say here in molecular dynamics, what we want to do is we want to predict, we have an initial state of 3D coordinates of the small molecule and maybe some solid material. And we now want to predict after 1 femtosecond, where will the molecule be next? Like, where will it go? And that's what we want to do here. And now we have a graph neural network of this whole system. And we have it predict an energy of the current state. And we say that if maybe two atoms are much closer together than they could be in reality, then the energy of the system that we predict should be very high. And then if we see this energy is predicted as very high, then we want to move the atom coordinates apart. And yeah, we can, or we want to move the atom coordinates in such a way that the energy gets lower. And so we can train these energy functions which are graph neural networks just predicting a single number. And after we've trained these energy functions, we can differentiate through them and update our coordinates such that the energy that we predict is minimized. And this way, we can run a molecular dynamics simulation of where an atom should move. And that's useful or molecular dynamics, of course, super useful because we can predict some properties of materials if we know the distribution of where a small molecule ends up, and we can gain an understanding of how a small molecule interacts with a material or a protein or another small molecule. Yeah, and then there's also another work in this area, because you don't always have to just predict predict an energy to do molecular dynamics, right? You could also directly predict the next step. And there a big problem in molecular dynamics is also how to represent the simulation, how to represent the things inside of our simulation. And their coarse graining is a big problem, where we want to summarize maybe a few atoms into a bead of atoms, and then predict the dynamics of the speed, because it's a more robust representation, and we can then maybe make larger time steps and run our simulation faster, and are of course also much more computationally efficient. And this way we can speed up our simulations, and then we can end up with the simulating some crystals or some materials like over here. And as we already said, this is pretty important to gain an understanding of maybe how some catalyst in a battery behaves, and then we can build better batteries or better materials for solar cells. And with that, I would then ask if you have any questions.
Someone raised his hand. Yeah. Go ahead.
Yeah, it was a very interesting presentation and sounds a good tool for analyzing the chemistry. So I have a doubt. So you said about designing, generating the molecule, and then predicting the structure, right? So once you predict the structure, how do you validate it? What way we can use it? Because if you're coming up with new molecule, and the structure for the molecule, like how can we validate?
So these were actually two different tasks and applications, right? In one task here, we're generating a small molecule, and we're not interested in the 3D structure at all here. We're just generating this small molecule that maybe should have some properties, but no 3D coordinates. And here in the structure prediction task, there we're given a small molecule and like its graph or its connectivity, like its molecular graph, but we don't have any 3D coordinates. And now, just from this molecular graph, we want to predict the 3D structure that the small molecule could take on. And these are like not only one plausible 3D structure, but many of them. Is that helpful?
Yeah, yeah, probably a good insight. Thank you.
Great. No, thank you for the question.
Simon?
Hi. So yeah, thanks for the great talk. So so I would like to know, you mentioned in some slides that you talk about the learned potential function. So is it the way that you kind of reconstruct the potential functions, and then so by some sort of graph neural networks architectures, and then after you got the potentials, which is approximate, that you do some predictions, like in terms of the energies and all that? Is it the workflow that you mentioned?
The workflow here, right? We want to predict how do our coordinates change, how do I coordinates change? And now what you call workflow is that we train a graph neural network to just predict the energy of a state. So the graph neural network doesn't predict any coordinate changes or any coordinates at all. It just takes the coordinates as input and predicts an energy. And now, after we trained the graph neural network, we take this energy prediction, we take the gradient with respect to the coordinates, and then this gradient tells us how to change the coordinates at each step to minimize the energy that our graph neural networks predicts. Right?
Okay, so you are outputting, you're kind of approximating the energy directly, not only the potential.
Yes.
Not just the potential function.
The potential is the energy.
Oh, okay, sorry. Yeah. Okay. Because I read some of the reference, they have another meaning. So like you are considering like DFT computation. People have the so-called exchange correlation potentials, right? And then they kind of they approximate the potential, and then they do the Kong-Sham solver, and then they have a whole flow, and then so they are just make use of the neural network to approximate the potential function. But I thought it was the same thing, but it wasn't actually.
I see. Yeah. So here we're talking about potentials, like we can obtain them with DFT, like density functional theory calculations, but we're now not obtaining them with these classical algorithms, with this physics-based methods. Instead, we're obtaining the potential with a learned graph neural network that predicts us the potential. Yeah. And then we use that potential function to do molecular dynamics by backpropagating through it and predicting coordinate changes.
Okay, thank you so much.
No.
Nice question. There was one private question I had, Hannes, which is the accuracy and fidelity of these ML graph NN models compared to the simulation based on classical Newtonian dynamic equations. How do they compare?
Okay, this question, it's excellent, and it applies in basically all of the different projects or different papers that we've looked at. But the answer is always specific to those different projects and those different papers. So for which one should we go into that? Let's maybe talk about it for molecular conformer generation, right? There we could
how about the one with the drug discovery, just because it's more simpler for me as a novice when you're trying to just or the one where you talk about let's say that it's going to create a problem for the viable drug, because if you generate something wrong, that could kill somebody, right? So just curious, how do you sort of navigate the uncertainty behind these predictions and trust the model? So yeah.
Oh well, you definitely should trust the model as little as possible. And after you have a prediction of your, like if you're generating a drug, right? Let's maybe talk about halicillin. There we propose now these drug candidates, but we definitely don't blindly trust the model. We instead go ahead and go through all of these suggestions, and only if it actually works, if it actually kills the bacterium, if we then can go ahead and do maybe some tests on mice and see that it doesn't kill the mice, it only kills the bacterium in the mice. And then we maybe do some more tests and then we can come into clinical trials, and humans try to use the antibiotic. We find out the antibiotic is completely safe, and then we end up with this final health. But also some of these methods, like AlphaFold here, right? They come with confidence predictions of how good their prediction is, or confidence estimates of how good their prediction is. And yeah, practitioners find these very useful and can then go ahead, and if AlphaFold predicts a structure but only with a low confidence, they can say, yeah, let me not even consider this prediction. Is that already clearing up everything, or would you also be interested in like how do these methods, most of these machine learning methods, compare against some classical methods in the sense of
just one sentence on that, because I know we always, say multi-physics and is the traditional way, and it's worked for for a while here, and now we're introducing these. So if I have like a set of proteins and we want to know how they're going to bounce off of each other, and you compare the initial state and the next state between these two, will they exactly be the same? Will they, what will, those bouncing balls, will they look exactly the same, or will there be some variability between the two? What's the sort of for the simple novice in me, how will that bouncing ball look like if one was using physics versus ML models?
Yeah, there's always a trade-off between time and accuracy. So if we were to run the perfect simulation with a complete quantum mechanics simulation of how these two molecules interact with each other, then this wouldn't finish until the end of the universe, but it would be completely accurate and exactly what's going to happen. But if we now make this faster, we can make some approximations and only use some heuristic functions. And then this works a little bit faster, but with less accuracy. And then we can make more approximations, and then maybe have a quite fast method already, but it doesn't have a high amount of accuracy. And this is what we can all do with some classical physics-based methods. And now the machine learning method maybe comes in at a particular point of the spectrum of speed. But then we have to see, like, if it is this and that fast, we have to see, is it more accurate than the physics-based method that is at that level of speed, right? And yeah, then we can hopefully be more accurate while being just as fast.
Got it. Yeah, and so it sounds like both of them together would be good, solutions. It's not one or the other, and also as computation speeds up, quantum, maybe the physics-based simulations will take over again. So it's probably change over time. Yeah. Thank you very much.
Really good question. Anything else, guys? Feel free to ask Hannes now. Otherwise, you can reach out to him via his LinkedIn profile or Twitter. Where are you more active, Hannes? Twitter?
Gmail.
Okay,
Gmail.
Okay.
That's where I'm definitely the most responsive, but I check LinkedIn and Twitter every now and then as well.
Yeah, cool. Right. If you have any more resources, Hannes, that we could share with the participants, I'll put that in the private community. And feel free to forward them. Any other videos that you would recommend?
I'll do that. And one resource that I would definitely recommend is our new paper DiffDoc that we made public 5 days ago, something like that. If you want to check that out.
Excellent. If you send over the link, I'm also happy to include that. With that, Hannes, thank you so much for the interesting talk. Hope to see you in the second part in the future. And with that, we'll close the session. And there's one question: if someone can get the presentation or the slides, I assume, is that possible, Hannes, or not?
Yes, that's absolutely possible.
Cool. Send them to me, then I'll upload them in the community.
Thanks,
All
and
right.
see you, everyone.
Bye bye. Take care.